Last video, a zero was just a number you plug in to get zero. True, but that hides something beautiful. Every zero is actually a place on a graph, the exact spot where the curve crosses the x-axis. Once you can see that, you'll understand at a glance why a parabola can have two zeros, one or none at all. Let's make zeros visible. Quick plan. A polynomial isn't just an expression, it has a shape when you graph it. Today, we'll graph linear, quadratic, and cubic polynomials and discover one simple rule that ties everything together. The zeros of a polynomial are exactly the points where its graph touches or crosses the x-axis. We'll go shape by shape, slowly. Start with the simplest. A linear polynomial like iy equals 2x plus 3. Its graph is a straight line, always. And a straight line crosses the x-axis at exactly one point. For y equals 2x plus 3, that crossing happens at x equals minus 3 over 2, which, remember from last video, is exactly the zero of 2x plus 3. So the zero of a linear polynomial is just the x-coordinate, where its line cuts the x-axis. One line, one crossing, one zero. Now a quadratic, like y equals x squared minus 3x minus 4. Its graph is not a line. It's a lovely U-shaped curve called a parabola. Here's a handy rule. If the number in front of x squared is positive, the parabola opens upward like a smile. If it's negative, it opens downward like a frown. And just like before, the zeros are where the curve meets the x-axis. For y equals x squared minus 3x minus 4, the parabola crosses the x-axis at x equals minus 1 and x equals 4, the very zeros we found last time. Seeing it makes it obvious. Now the cool part. A parabola can sit in three different ways relative to the x-axis, and each gives a different number of zeros. Case 1. It crosses the x-axis at two separate points. That's two distinct zeros. Case 2. It just touches the x-axis at a single point, balancing on it. That's 1 0. The two zeros have merged into one. Case 3. It floats entirely above or entirely below the x-axis, never touching it. That's no real zero at all. So a quadratic, a degree 2 polynomial, has at most two zeros, never more. That's the headline. Let's go 1 degree higher. A cubic like y equals x cubed minus 4x. Its graph is a wavier curve, and this one crosses the x-axis at 3 points, x equals minus 2, 0, and 2, so 3 zeros. Other cubics might cross fewer times. Y equals x cubed touches at just 1 point, 1 0. Y equals x cubed minus x squared crosses at 2. But a cubic never crosses more than 3 times. And that reveals the big general rule. A polynomial of degree n has at most n zeros, because its graph can cross the x-axis at most n times. Degree 1 at most 1. Degree 2 at most 2. Degree 3 at most 3. Simple and powerful. Quick check. Read it off the graph. A polynomial's graph crosses the x-axis at exactly 3 points. What's the least degree it could have? A, 1, B, 2, C, 3, or D, 4? Think about the rule we just learned. You have 10 seconds to solve this. Pause if you need more time. It's C. If a graph crosses the x-axis 3 times, it has 3 zeros. And since a degree in polynomial has at most n zeros, you need degree at least 3. A degree 1 or degree 2 polynomial simply can't cross 3 times. Your turn. A parabola opens upward and sits entirely above the x-axis, never touching it. How many real zeros does that polynomial have? A, 2, B, 1, C, 0, or D, 3. Drop your answer in the comments. A, B, C, or D. I read every single one. So now, zeros aren't just numbers. They're the spots where the graph meets the x-axis, and the degree caps how many there can be. If this made polynomials click visually, follow Clarix. And in the final video of this chapter, we uncover something almost magical, a hidden link between a polynomial's zeros and its coefficients. So you can find the sum and product of the zeros without even solving for them. That's where it gets really powerful.